Hello, hello. Sorry for the delay. Sorry for the hello, hello. Sorry for the delay and bear with me for one more second. Okay, I'll be right there. Thank you for your patience. Um, what- sorry. Okay. Um, sorry, there's a lot going on. All right. Hello. Okay, so do I get some hellos though? I mean, I'm late, so I don't get any hellos. What's going on? So hello. Well, I'll say thank you, Yaneli. And I was going to say Yaneli because I see your face, sort of. So hello, Yaneli. And good afternoon, Gabriella. Here we go. Okay, here we go. But it's my fault. I'm like, well, I guess I did say hang on, didn't I? So why would you say hello? Good afternoon, Kaya. Good afternoon, Yaneli. Good afternoon, Genesis. Good afternoon, Gabriella. Good afternoon, Sydney. Good afternoon, Erica. Good afternoon, Ariana. Oh, and there's Kaya. Thank you. Double Kaya. And there's Skylar and Sonam in the world of avatars. Okay. Hello, hello. All right. So, in a way, there's a lot to talk about today, and in a way, not. I am not going to try to cover anything particularly shockingly new today. I mean, not new topics or anything, but I think there's a lot of loose ends to tie up or matters to clarify from the lab discussion we've been having, the discussion of lab 5, the discussion of the rough inclined plane. Let me be a little bit more. Well, first of all, let me ask you, let me clarify. Have you turned in yet your formal report for lab 5? No. Okay. Thank you, Kaya. All right. Perfect. Thank you. And that's points and all that. All right. So then because as I've mentioned, because this is a big problem because the problem of lab 5 captures a lot of physics and a lot of physics that does appear in the final exam. Like, I think it's very worth being as clear as possible and as thorough as possible as we can be with all of this physics. So last Monday, I was trying to walk through various aspects of this lab number 5, right? Then you watched a couple of videos that I hope you saw. They're not directly about lab 5, but they were very related to the concepts underlying lab 5. Um, and then I got a bunch of good afternoon, Andre. Good to see you. I got a bunch of questions in the portal after you watched the videos. I got a bunch of questions, or things that you were still concerned about the concepts in the videos, many of which relate to this lab. So those were great questions, and I hope I made it clear to you um, in your portal that they were great questions. So what I want to do today mostly is try to address these questions and straighten out the things that still seem to be confusing about inclined planes. And again, hopefully this will it'll help you write your lab reports and get a better grade on the lab reports, in addition to everything else. And good afternoon, direct chat person. Thank you. I appreciate it. Today is mostly about, to be honest, well, it's not even that. The equations on the board are what I would get to if I get to all of these questions first, but in the last class I did not. So really what today's about is this. Um, so in principle, I'm picking up where I left off last Monday and helping you analyze the situation in lab number 5, the rough inclined plane, where something goes up and then it comes down. And the ultimate goal of that lab, the ultimate conceptual goal, was to analyze why is it that something seems to take less time to go up a rough inclined plane than to come down, right? Like that's the ultimate thing of the whole lab. So I'm going to try to review that quickly, but then in order to understand that, you have to do all these diagrams and you have to break up all these vectors into components. And then at the end of the lab, you're supposed to actually plug in all these numbers and take all this data that you got and actually solve for a value for mu, for the coefficient of friction. And that whole process led to a lot of questions that I want to address today. So this is very much about you. Like, this is not a straight up lecture. This is me trying to address questions, which means all the more than usual, you should feel free to put a ton in the chat or raise your hand or, or speak your mind, because I'm really here trying to help you straighten out these ideas for your lab, for your exams, for the rest of this course. So let's please take advantage of this time. I mean, consider this more recitation than lecture if you like. I'm going to say two more things to that end before I get so really, like you should put questions in the chat, or you should tell me when you still don't understand what I'm saying, or that I need to make a left turn somewhere or whatever. To that end, I'm also going to say, since I just did this in the last section and there are so many questions, I'm going to try to cover different questions in your section from I'm not necessarily, you should watch both sections when you get a chance. You should watch both recordings because I'm going to try to not make them redundant. Okay. There's questions I didn't get to in the other. There's questions I'm going to skip right now and just get to yours. So you should watch both, especially before you turn in your formal lab report for lab 5. Uh, But last thing I'm going to say before I get rolling on this, hold on. Okay, this is a dangerous thing for me to do. Um, I'm writing this in the chat to sort of save a lot of time if it because I still don't have your midterms back, right? Okay. Well, someone's here. And I, I don't want to spend another period talking about that fact, but I absolutely recognize that some of you may be getting nervous about your grades or your grading information. Also, I have a complicated way of it. Like, even if you look at all the information that you're getting from Google Classroom, like it's absolutely true that whatever Google Classroom is computing as like your grade right now, like that's not, I mean, it's not really meaningful because Google Classroom doesn't know how to add up all the points the way I do and all that kind of stuff. So I'm going to try to be as concise as I can. If you are still in this class and still working with me and paying attention, and you did your whole midterm exam and you did it on time and you did it honestly and thoroughly and stuff like that, and you're doing homework and you're submitting game portals, right? If you're a person who's still trying to do what you're supposed to do in this class, but you're nervous because you're still waiting on grading information, or you're just nervous, or you feel like you don't know how, that you might have struggled on the exam. Okay, so first of all, I totally understand that. I'm totally with you. That's fair that you would be nervous. And I would like to reassure you that if you've I'd like to reassure you publicly, but I also will reassure you personally. I'm going to try to catch up during this break and get the exam information back to you as quickly as possible. Of course, that would be the most reassuring thing I can do. But let's even say that you get back your grade on the exam and it's lower than you were hoping, or lower than you were expecting, or lower than you think it needs to be. Okay, I just want to encourage you at some point, text me and just say, I'd like 15 minutes to talk to you on the phone I mean, phone is probably even will be able to make a time even more easily than Zoom or something. If you just want like 15 minutes or 20 minutes to talk to me on the phone so that I can personally say to you like what's happening with you in the course and like how or where I think you are or how I think you should be less worried than you might be, right? Or maybe depending, and I might be in the car during the conversation, so I might not be able to be looking at your exam during that moment, but I might not be. I might even be able to informally look at your exam like while I'm talking. Okay, if that will help like lower your nervousness in any way, to just have like a 15-minute like direct touch base with me about what's going on with you in the class, I'm happy to do it because what I'm here to say to all of you in general, if you're that person, and this was like a big deal in the other, you can play the section of the class and you'll see I'm like trying to address this in detail for like 40 minutes and it probably gets really boring after a while. But I'm here to say, if you're a person who's doing everything that they think they're supposed to be doing, if you're trying and turning in the homeworks on time and you turned in your exam on time and like all that stuff, and you're here in class every day, but you're worried how it's all coming out in the wash, believe me, you have less to be worried about than you think. Less to be, and I can tell you that more directly depending on who you are. If we make a quick phone appointment, like I know your work, a lot of you, I know how hard you're working, a lot of you, I see in the fact, and I know that you're still confused about my grading system. I mean, generally people are. The thing I just want to remind you as we get closer to the end of the semester is the grading system is confusing because it's unusual. Not I don't want it to be confusing. If I have to take 15 minutes on the phone just to explain the grading system to you again, I will happily do it. The grading system is designed so that people who work very hard and try and do everything they're supposed to do, even if they struggle on exams, even if they have even if they struggle on exams or they struggle on the first exam and it doesn't come out the way they want, there's still a lot of numerical cushion in their grade so that your final grade at the end of the semester will come out higher than you might think looking at an exam score like that, right? And of course it would help if you had your exam scores back. I know that. But I'm saying, again, I don't want to like dwell. I'm saying if you're doing your work and you're trying, I respect that you're probably the person who is nervous. It's people that are trying that are nervous about where all their efforts are going. But if you're that person, I can't make you unnervous. And the way I'm yelling like probably doesn't help either. But I'm saying the grading system is designed. The disadvantage of the grading system is it's confusing. And Google, I can't program it into Google Classroom, so you like can't tell exactly where you are while you're. That's the disadvantage. But the advantage is, first of all, it's the exact same system for 204. So if you have me again for 204, then you're used to it by then. And you'll see by the end of 203 that if you've been doing everything you're supposed to do, probably the grade you get at the end of 203 is higher than what you think it's going to be based on your exam results. That's like the best thing I could say for, again, that doesn't mean everybody's going to get an A, but it does mean I'm perfectly happy if everybody does. It does mean you're not competing for A's. It does mean a lot of people do get A's. It means maybe you're going to get a B, like if you really struggle on the exam, maybe you're going to get a B, not an A. If you're doing all your work and all that kind of stuff, I'll talk to you personally if you want. But if you're worried about failing, whatever that means, if you're worried about a C minus or a D or an F, okay, that does happen to people. That can happen in this class. I'm not saying it doesn't. That means two things. That means one, if you get a B or an A in this class, it's not a gift. It is not a gift and it's not a mistake. And it means you did a lot of work in this class. It means I'm not Einstein and neither are you. Neither one of us is a Nobel Prize winning physicist at this point in our lives. But if you're being graded as a physics student, then if you get an A or a B, it means you were a great physics student. And maybe taking exams was your strength. Maybe it's not. But there's more than one way to get an A or a B in this class. Exams is just one way. All the other work is another way. Okay. So if you get an A or B, it's not a gift. It's not a joke and it's not a curve. It's credit where credit is due. If you're worried about a C minus or a D or an F or something, I'm not saying those don't ever happen. They do, but they're not happening if you're one of those people that's been doing all your work and you're nervous how the work is coming out. That's not where the C minuses and the DFs go. And I'm not saying this with judgment or as an insult, but where there's going to be C minuses or Ds or Fs, more likely is the people that are, I mean, and I'm saying this again respectfully, more likely it's not the people that are nervous how all their work is being judged by me. It's the people that know in their hearts that they haven't turned in a lot of work for whatever reasons, or who aren't even still here in this discussion paying attention right now, or whatever reason. Could be a medical reason, could be a family problem, could be mental health reason. Like I'm not like there are reasons that some other things in life take priority over engaging in this class. I totally get that. So I say respectfully, will some people have to take this class again? Yes, invariably that does happen. If someone has to take this class again, it's not the person that's been turning in work, or whatever. It's not the person that is sitting here sweating buckets over all of the work that they've done. It's the person that knows that something else is going on in their life where they haven't been able to engage in the work or with me or in the Zooms. And that I'm not, and therefore, if you're a person who does end up taking this class again, I'm saying this with total respect. If you're a person that knows in your heart you really have like you didn't turn in the exam on time, you really haven't done any homework, whatever, right? First of all, you should reach out to me so we can get some communication on this. But second of all, if it turns out that you just are not, or they're just not even here right now, if you're a person who just cannot be engaging in this class this semester for whatever reasons, and it ends up that you have to take the class again, I will welcome you with open arms and we will just take chew on the situation and we will both make it a point to try to make sure that you don't have to do a third time. And we will do it like compassionately and powerfully. I have had to take classes over in my life. It is not a crime or a shame. Things happen. And sometimes people just I needed to hear certain physics over and over before I understood it. It's why I teach. I get to hear it over and over before. So, okay, long story short, longer than I meant. You could hear the even longer version if you play the other class. I mean, there's other, okay, but if you don't, if you're nervous in any way, but you've been doing the work, text me. We'll make a phone appointment and we'll see what's what. There's not a promise of an A, but there is a promise that if you've been doing respectable work, you will walk away with a respectable outcome in this class. Like that is a promise. Okay. So I hope that makes any sense. Oh, and hello, Joran. Hello, Joran. Okay. I hope that, and if you're not nervous, don't let me make you nervous. I'm not here to make you more nervous, but just it is that time of year is all. Okay. So should I move on? Should I go back to physics now? Can I just get like any affirmation or any? Oh, can I move to physics? Is anybody left in the room? Oh my God. Wait, have I been on mute this whole time? Wait, could just someone affirm? Can I move on? And can I go to physics now? Thank you, Yaneli. Thank you, Samantha. Thank you, Sydney. See, that's little moments like that. That's like these people. You're okay. Thank you, Kaya. All right, all right. Thank you, Samantha. Or did I say okay? Okay. So I'm gonna go physics now. Sorry. And thank you, Gabriella, and thank you, Sanam. Okay. Okay. Drama. Okay, so picking up where we were in the lab. And here too, by the way, okay, I'm gonna try. I think the lab is hard. I think it's big. I think it's important. I think I got all these cool questions from you and the thing. But if you could send me direct chats that say, no, we get this. Can you please speed up or go to this other question? You can do that. You should do that. Okay. The summary conclusion at the end of the lab, in a way, well, the big conceptual question of the lab, the big conceptual question is why does the thing take so little time to go up and so much time to come down? That's a surprise. None of us would have expected it, but it's true. So the big thing that we tried to explain last week that I'm happy to re-explain here or not is that if you really carefully draw all the diagrams, if you draw the system schema, then you draw the pure free body diagram, then you break up forces into components and draw the component free body diagrams, you ultimately see that on the way up, both forces are working together. The gravity component of force and the friction component of force are working together. So they're adding together. So they're producing a really big net force while you're on the way up, which produces a really big acceleration magnitude on the way up, the plus sign at the bottom. So the conclusion after all of this analysis is the conclusion in yellow at the bottom of this page, that the acceleration magnitude when you're on your way up is a huge magnitude. Two factors working together, the gravity factor and the friction factor working together. Whereas on the way down, gravity is in conflict with friction. They're working against each other. So they don't add together, they subtract from each other. So you get a very low magnitude of acceleration on the way down. That ends up meaning that you take a lot less time to go up than to come down. Now, I'm going to say this. That's still a hard point. There's still a lot of details behind that point, and it is your job to explain it like a lot in detail in your lab report. I'm going to say right now that that whole business of exactly I'll just say quick. For example, people get confused. Like I keep saying, on the way up, all the forces are working together, which is true. But people get very confused because they're like, wait, I thought on the way up the forces are working against you. Like you're going up and all the forces like seem to be pointing down. So why does Yaverbaum keep saying the forces are helpful when they're working against the motion on the way up? Good point. That may be what's confusing some of you, unconsciously or consciously. If that's your issue, I spent a lot of time on that in this morning's class. So play that video. I want to get to the questions that you guys specifically asked me in the report. So I'm going to skip that right now. But if that's your issue, there's a lot of discussion of that in the other video. Please play it, like once I post it. This morning, okay? Furthermore, I'll also say that a big issue that came up in the other class, a big issue is how the pluses and minus signs work. Like even people that think they're conceptually understanding what I'm saying, like in the end, still, for example, don't see how once you plug in all the numbers and you solve for mu at the end of the lab, a lot of people legitimately ask, like, wait, I get this, or I thought I got it, but then I plug in all the numbers to solve for mu, which we're supposed to do at the end of the lab, and I keep getting a negative value for mu. A lot of people said that, primarily in the other section. Great question. Great question. I will say right now, I discussed that in detail in the other video. So if that's your concern, even if you didn't write it to me, if you're not sure about how the pluses and minus signs work, like really when you get into the numbers of this lab or of any of this, watch the other video. The punchline is make all the numbers positive. I mean, that's the punchline, is that we're setting up a coordinate system where down is positive, whether you're moving up or down. So like all the numbers that you plug in, including A, when I say the acceleration's bigger on the way up than on the way down, I mean bigger. Like these are all like, it's a positive number that's big on the way when you're going up, and it's a positive number that's small when you're on the way down. Definitely don't switch the way you do positives and minus. Don't switch the way you do it from up to down. That's a real mistake. And some of you may be doing that. It's a classic mistake. It's an understandable mistake, but it's a mistake. And furthermore, I'm saying don't call down negative. Sometimes that's a good thing to do. It's not a good idea to do. Anyway, watch the other video. Make all the numbers positive, and you'll see that mu will come out positive. Okay, but then to get what I want to get to, yeah, so this is all like, you're going to have all these notes. If any of those notes address anything that you're wondering that doesn't come up to me, look at the notes. But now a question I saw over and over again in your class portals, because you watched the video carefully, thank you. And many of you noticed that at least one of the videos focused so heavily on the whole idea of gravity, right? On the mg. It didn't even deal with friction, one of the videos. That's right. One of them was just really trying to focus on why are we breaking up mg the way we are? How do we get the sine and cosine? And like, it doesn't even have to do with friction. It doesn't even have to help you with the friction part. It's just what we're doing with gravity. And whatever we get out of that video, whatever we're doing with gravity is still true, even when we add friction to it. But some of you had a lot of questions about the gravity. So I'm going to focus right now on just the end, specifically what a lot of people ask me, a lot of you ask me is, why is sine on the x-axis and cosine on the y-axis. I always thought sine went with y and cosine went with x. Very fair. Very common, very fair question. So let me try to address that now. And then some of you asked versions of that. Like, I sort of get what's going on for this lab, but I don't think I could do I don't see how I could do other examples or what I'm supposed to do with this, like if it were on another homework or an exam or something. Okay. So, 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 okay. So the thing I'm here to address, yes, yes. Oh, wait, I forgot what's yes. Wait. Oh, yeah, yeah, yeah. Okay, 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 okay. Um, Um, so I'm here to just focus. So I'm not going to, so if you want more of a focus on friction, that's the other video. What I'm going to focus on right now is just this whole business of breaking up MG. Like, why are we breaking it up at all? And specifically, why did sine end up on the x-axis? Like, that confuses a lot of people. Okay. So that's what I want to show you. Okay. So, okay. Sorry. Okay. Okay, so imagine, so I'm isolating, I'm just trying to focus on the issue of gravity, so I'm not even worrying about friction now. I know I've said that. But remember, everything I'm going to say about gravity now will still be true if you just add friction as the next piece. Like it's all like one piece at a time in physics. So so if you imagine like this smooth inclined plane, like friction zero, and your marble or your block, whatever mass m happens to be going up right now, it could be going down. It's going to be the same thing either way. If there's no friction, if the plane is tilted according to that picture, then the pure free body diagram, I hope it's clear. The pure free body diagram is that mg is certainly pointing straight down, and the normal force from the track is pointing off at an angle perpendicular to the plane of the track, right? That's the pure free body diagram, right? Now, we look at that, and like what we want is to be able to do F net equals MA separately along each axis. We want this is always true in physics, like we want to apply F net equals ma, which is a vector equation, right? That means, I mean, in order to solve for A, we want to add up all the forces and solve for A, but it's a vector equation. That means that it applies to each dimension independently, right? In other words, we want to do sum of the forces on the x-axis equals mass times acceleration along the x-axis, and sum of the forces along the y-axis equals mass times acceleration along the y-axis. That's what we always want to do in physics. But that means we need to see all the arrows along one axis and all the arrows along another axis. That is not what we have in the situation right now. We don't have two clear axes. So the first thing we have to do is choose, like, we're going to break up one of these forces. We're going to break up one of them. We have to break it up into X and Y components. In order to break up into X and Y components, we have to choose what the X and Y axis are, right? So the first thing, what the whole video is trying to show, and hopefully I'll get back, it's trying to make a compare. What it's saying is it may be confusing to break, it may seem confusing at first to break up mg. You might think at first, why would we break up mg? Like the normal force is already a diagonal line. It already looks like a hypotenuse. Why don't we break up the normal force and leave gravity alone? Why wouldn't we do that? Well, what the video is trying to show is that it's not that you can't do that. You can. The whole point of Galileo is you can choose your x-axis. You could choose your x-axis to be this or this, right? Physics will work either way. But the reality is that if you choose your x-axis to be horizontal and therefore leave gravity alone and break up the normal force, it ends up being a lot more mathematical work than if you tilt your axis in your head, if you tilt the x-axis to line up with the plane, therefore tilt the y-axis to line up with the normal force, and then break up gravity. It seems weird at first to break up gravity, but it makes for a lot less computation because, well, I'll write it down. we we have to break up something so that its components lie, so that all components lie along an x-axis and a y-axis. So we have to choose our x-axis and y-axis. We could choose anything, but the strategy that I said last week, and stop me if this doesn't make sense. The strategy is you choose an x-axis that lies along acceleration. I'm going to write that. Well, I'm going to say it and then I'm going to write it down. We're going to choose an x-axis that lies along the direction of acceleration. We're going to align positive x with positive a so that we have as few sines and cosines to deal with as possible. Because I know for a lot of you, what you really want me to get at here, what you really want to see is why did sine end up being where it was? Like a lot of you are thinking, I get it. I think a lot of you are thinking, I get it. But where I need help is how did you assign sine to x and cosine to y? Like that's where I'm stuck. I will get there. I hear you, but let me say that one of the reasons we're breaking up And you might even, some of you might be thinking, if it hadn't been broken up gravity, like if you'd broken up the normal force, then I would totally see how to do sine and cosine. But it's this breaking up gravity thing that makes the sine and cosine seem really weird. It makes it seem really weird. But let me tell you, if you didn't break up gravity, the point of the video is that the other video is that if you broke up the normal force, you'd have 3 times as many sines and cosines to deal with. You'd have to make the decision 3 times, and that's what we're trying to avoid. This is one hard decision that I'm going to show you, but the reason we're breaking up MG is that there's only one hard decision instead of 3. That's like the big punchline of, okay, so bear with me as I show you why we're breaking up MG, and then I will show you where is the sine and the cosine. Um, I have to do that. Okay. So first of all, I'm saying if you choose if you tilt your head and choose an x-axis that lines up with the direction of acceleration, it means that you don't have to break up acceleration into sine and cosine. I mean, to cut to the chase. So that's what I'm going to do. So whatever difficulties you have with sine and cosine, we're going to have fewer of them if we break up MG. So now here comes the breakup, so to speak. Should write a love song. Here comes the breakup. Here is MG, right? In fact, I mean, that's true, but hold on. And let's put up here, just a reminder. The plane looks like this, right? Like this is the plane. The theta is measured from the horizontal. And this is a right angle right here. Okay, so gravity's pulling straight down. So we're going to break up gravity. That means we're turning the gravity itself into the hypotenuse of a large right triangle. We're asking what are the two legs of gravity? We're asking what are the two jobs that gravity does? In like 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 this is gravity, right? But we're tilting with yeah. So gravity's pulling you straight down the plane. That means it's doing two things with regard to the plane. It's pulling you along the plane and it's pulling you into the plane, right? Like to some extent, gravity is going like this. And to some extent, it's going like that. That's a right angle right there. Right? Like I'm zooming in. I'm saying the two legs of this triangle, the two perpendicular components of gravity are the two jobs that gravity, the two implications of what down means when you're on a slant. What down means when you're on a slant is down along the slant, as well as down into the slant, down against the slant, right? Or put another way, let me just make this not changing it, I'm just making it slightly new. Like by gravity pulling you, by the earth underneath you, pulling on you straight down, that, first of all, that causes you to stay in contact with the plane, right? But it also causes you to roll along the plane. The two jobs that gravity is doing, the two jobs that gravity is doing are, I'll write it like this. Right? Just like southwest really means or equals some amount south plus some amount west, right? Down, when you're on a tilted plane, tilted towers, 360 no scope. When you're down, when you're being pulled down, you're being pulled down along, plus at the same time, you're being pulled down against. Like, what is right? Like, and you should really, in fact, I want someone to say in the direct chat or somewhere in the chat, either say, yeah, I get that, or say, no, that's exactly what I don't get. Like, somebody tell me, I'm going to say it one more time. Do you get that down means some amount down along and some amount down against? Like, gravity is doing two jobs. It is accelerating you along the plane, but it's also pulling against the normal force to keep you on the plane. Like, could someone say yes or no to that? Thank you, Kaya. Oh, and thank you, direct chat person. Okay, cool. That's good enough for me. 1 and 1. All right. So what I'm assuming right now is that or I'm not assuming, I'm inferring from Kaya and a direct chat person that this diagram, well, I'll make it more, this, and you wanted, like, this is not just a raw triangle with just like sides of a triangle. These are vectors, they're arrows. I'm specifically saying that down is the sum of down left plus down right, if you want it like that. And one of these is sine of theta, and one of these is the cosine of theta. And the question is which, or how do I know which is which, right? Like, this is where I think most of you like want to know what the heck is going on. Like, but it's you in order for, so I want to answer, like, why did I do the sine and the cosine the way I did? But I really want to it's always like this in physics. You might think that your issue is why is one sine and the other cosine. But it really might be very possible that your issue is coming before that somewhere and you don't realize it. So really, if you're interested in the sine versus cosine thing, welcome to the physics club. Yes, that's a real good question. But please look at this picture first before I go any further and make sure that you really could draw this picture on your own and you would in the lab and you really understand why one of them is a sine, the other is a cosine, and it's not any other picture. Because if you do understand that, then look, to get this triangle that I just drew, right? What did I do? Like, where's the inclined plane in this triangle? That blue thing is the inclined plane, right? Tilted. In other words, well, yeah, like that, like, what am I trying to say? Yeah, well, that's what I'm trying to say. That blue thing that I just sectioned off, that is your inclined plane, but rotated by an angle theta, because we rotated our head by an angle theta to, right? Like, we were looking at inclined plane. We originally thought the tabletop of the lab was the x-axis, but then we rotated the x-axis in our mind. We rotated the x-axis up by an amount theta to match the slant of the inclined plane, right? So once we're looking at it that way, the inclined plane has rotated in our mind by the angle theta. I don't know if that makes sense yet or not, but so far, part of what I'm trying to say that this thing is the inclined plane, right, with theta over there. Like if you just take our inclined plane and yeah, if you just take our inclined plane and rotate it down to match our diagram, you find that Um, the angles to the left, the right angles to the right. Um, I don't know how else to say it. I don't know how else to say it. Let me just think for a minute. But I do know how else to say it. Maybe this is even better. Uh, It's not a contradiction. Maybe like, where did I get that? Why am I saying that? Put it this way. If you literally look at the inclined plane, if you literally look at the inclined plane, yeah, let me do it. This is even better. If you can't erase, you can't erase. It's before you even tilt your head, just look at the inclined plane. It's a diagonal line. I, I'm saying if you look at the inclined, here's the inclined plane, straight up without any rotation, right? Like, like, like there's the inclined plane, like it's matched perfectly, right? Horizontal leg, vertical leg, hypotenuse going down, right? So if that's the inclined plane, that may be more clear to a lot of you. No rotation, nothing. That's the inclined plane right there. And the angle is indeed right here as it should be, right? Like if I'm just copying the inclined plane from above, then the angle is right there between the horizontal and the slant. But now, if that's the inclined plane, right? If that is the angle theta that you measured in the lab right there, well, then then this thing, I'll change the colors. Then this thing here is not theta, right? If that's theta right there, this is what I should have said from the start. I think this is probably clearer to a lot of you. If that is theta right there in the blue, then this red thing is not theta. It's the complement of theta, right? Because together, that red angle and that blue angle make a yellow angle, the yellow right angle. Together, they make 90 degrees, right? So if that is the complement of theta, but if this is a right angle right here, all the angles of a triangle must add up to 180 degrees, right? So if that blue thing is theta, the thing next to it is not theta, but 90 degrees minus theta, then this thing that, whoops, sorry, then this thing down here, like if the red thing is 90 minus theta and the red right angle is 90, because all right angles are 90, then the missing angle down here must be theta itself. I don't know if that helped anybody, but I'm saying this angle down here, that's the same angle as your original angle that you measured in the lab. That's the first point I'm making. That once you look at your vector triangle, the angle down at the bottom of your vector triangle is the same as the angle measured from the horizontal in your lab. Now, so what? Here's the big so what. People think, and the reason everybody's confused is people think sine always goes with y and cosine goes with x. That's just a misunderstanding. I mean, it's very common. You're not crazy for having it. There's two reasons but it's not true. It is not, there's no law of math or science that says sine always has to go with the y-axis and cosine has to go with the x-axis. There's two reasons you think it's true. You're not crazy. You're not dumb. Everybody always thinks that. The reasons you think it's true that sine always, wait, hold on. I'm going to stop right because this is the real, I want to make sure everybody hears this because this is like what everybody asked about. And it's totally fair. I sound all upset. I'm not upset. I'm just like trying to be clear and I'm glad that everybody admitted that they were confused about this. So wait, I'm going to explain now why sine is not the y-axis. It's not a rule and it's not true in this case. But before I explain it, and I'm going to explain it two ways, maybe three. Before I explain it, I want a show of hands. Are you with me right now? Like, do you know that I'm about to explain the sine y cosine x thing? Like, give me an electronic hand or a yes in the chat or something. Okay, thank you. That's good. Okay, that's awesome. Oh, I love this class. I'm going to miss you people after you kill me. Okay, great. Thank you, all of you, Kaya, etc. And I can't even see who it is anymore. But yes, Alfred, thank you. Yes. Okay. So first, let me tell you why you think that. because it's not your fault. Like, you're not dumb. I thought that too forever. I hated this thing forever. Believe me. Why do you think I make a big deal of it? First of all, you think sine always goes with y because it always has up until now. You're not crazy. Almost every time it's come up in a math class, or maybe a science class, but usually a math class, like it always does turn out to be that sine goes with the vertical. It does. But that's because we've never had to tilt our head before the way we're tilting our head now. We've just always had really convenient, nice triangles where they were just lined up with the x-axis conveniently. And then we always measured our angle. Like it was on purpose to make things clear and consistent that teachers and others of us set it up that way. So this is the first time that things are hard enough that you actually have to think a little bit out of the box. That's number one. But number two, the other reason you probably think that is also because you're not crazy. Because in the unit circle, which I do love, in the unit circle, yes, sine is defined to be the y coordinate, and x is defined to be the and cosine is defined to be the x coordinate in the unit circle. And yes, the unit circle is awesome, and I love the unit circle, and it's going to be a big deal in physics 204. So I'm not saying forget the unit, but that is different. It's not saying that sine always goes with the y-axis. It's saying specifically that the sine of the angle in the unit circle in that specific setup is the y-coordinate in the unit circle. So that has been planted in your brain and is probably affecting you legitimately here. But here's the deal. The real deal is, what is sine really, really always? Like, what is sine that will never get you down, that will always be right, even in the unit circle or in all the other cases? The thing that sine really is opposite over hypotenuse. And cosine is adjacent over hypotenuse, no matter where the opposite and the hypotenuse are. If you want to memorize anything that will never let you down. And yes, it relates to the unit circle and it relates to all your other examples from life. But the general thing that is always true is that the sine is the opposite over the hypotenuse. So now here we're in a case where we tilted our heads because we're being physicists and we tilted our heads. So if we look down, I'm going to just draw it again now more neatly. If we look down, zoom in on just this triangle, right? The axis along the plane. That's what that axis is, along the plane. That is opposite from the angle, the angle theta. Now, by the way, you might, so the conclusion, so I'm saying that one takes sine. Like, so therefore, if you call that x, I'm literally saying the sine of theta equals x over mg, if that sine is called x. Therefore, x, or let's be more specific, like mg sub x, like the component of mg that's along what we're calling the x-axis over the hypotenuse, which is mg. I'll make it more. Sine of theta equals the opposite over the hypotenuse. So that's mgx over mg. Therefore, mgx equals mg sine theta. And the other one is, mg cos theta for the same reason that the other one's adjacent. Now, two things. I mean, that's the answer. The answer is that side is opposite the angle. And that will never fail you, the opposite versus adjacent thing. Now, I'm going to still say some more about this because it is a real issue. First of all, if you're at the point in physics where your biggest concern is why is this one sine, and like I could do everything I can do, but I can at the final moment Yeah, like if you're even thinking, well, now I'm insecure. Like now, I guess I get it. But like now, if I had to do this on my own in some crazy example in physics 204 or something, I'm not sure I would know what to do. Well, what I'm saying is, first of all, what you would do is do SOHCAHTOA. You do which one is opposite, which one is adjacent. That will never fail you. But if your biggest issue in physics is this, welcome to the physics club. This takes some getting used to, but it means you understand a lot if this is what you're concerned about. It means you're in the right, like, again, you're not the person that's worried about failing this class if this is your biggest issue, really. But let me go further, please. Um, if you're getting what I'm saying, you might be having that typical physics sensation of like, okay, I get what you're saying to the point where I'm not even 100% sure why I was like, it all makes sense. But then why was I confused before? Because you keep saying I'm not crazy, but now you're almost making it seem like it's so obvious that I almost feel like I was crazy or I was stupid or something. No, 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 no. What's not obvious about this is like, first of all, yes, sine is always opposite. But notice, in order to get this right, we had to figure out opposite what angle. Like the thing that that we all blow past for years in trigonometry and stuff is like, you might never have thought about this consciously before. But of course, I could have picked the other angle in this triangle. I could have called the other, I could have like focused on the other angle and called it something else. And if I focused on the other angle, then of course the opposite and the adjacent would flip, right? Like what you might be noticing now for the first time is all of this opposite adjacent stuff. It totally depends on which angle you've chosen to focus on. And if you focus on and if that's always given to you by a math teacher or a physics teacher, then it doesn't seem like there's much to think about. But if you're thinking about it now for the first time, wait, what if we had chosen the other angle? Then wouldn't sine would be lined up with the other axis. That's true. That is true. The whole opposite adjacent thing all depends on which angle you choose. So how did we know which angle to choose? We wanted to choose the angle that actually is the original angle that we knew from the lab. That's why I just spent 15 minutes doing this weird geometry that might have lost some of you. I'm trying to say, like, sure, you can do SOHCAHTOA to either angle you want in a right triangle. But the one that we knew, the one that you measured in the lab that we called theta, is the one that ended up down at the bottom of this triangle. If we do the other angle, we could do the other angle, and then sine and cosine would flip. But remember, sine of 30 is the same thing as cosine of 60, sine and vice versa, right? The reason SOHCAHTOA works, it's the whole point of SOHCAHTOA is it's saying the two angles that you ever have to choose from are always complementary to each other because it's always a right triangle. The third angle is always a right angle. So whichever one you pick, you assign sine and cosine to it. If you pick the other one, cosine and sine would flip accordingly. The sine of an angle is always equal to the cosine of its complement. That's why this whole deal works. That's number one. So yes, it matters which one we chose. We're saying the bottom one in this case is the one that we were measured in the lab. That's number one. Also, and I'm just about done, I promise. I know I'm like yelling and screaming. The other thing is, again, like if you're saying like, yeah, but okay, it's fine. Like Yaverbaum, like fine. I mean, I got it sort of like I said, okay, so it's SOHCAHTOA, and I went and got a cup of coffee and I came back and Yaverbaum's still yelling about the same darn thing. Like, okay, SOHCAHTOA, but like still at the end of the day, like yada yada Yaverbaum, like whatever happened to sine being the y-axis and cosine being the x-axis, what we're really trying to say is this whole Galileo thing and this whole tilting art, the physics piece of all of this is what we're really trying to say is the x-axis is up to you. There's no objective x-axis. That's why SOHCAHTOA is better, because the reason sine, you can't say that sine always lines up with the y-axis, or that you can't memorize that cosine always goes up the x-axis, because it turns out in physics, the big choice that we have to make in physics is where's the x-axis? Mother Nature didn't tell it. Go to outer space. There's no objective x-axis in outer space. We're choosing an x-axis that makes our life more strategic. That's what we're doing. So of course, the sine is going to go wherever the sine goes. If I had called the other axis y, then it would be with what you want, which then leads to this. And I know we have 14. So wait, I'm going to pause for a sec. What I want to go to now is the other part of the video, the thing that was confusing people, like what was all the other business of like, why did I then in the video then scrap all this and break up the normal force? Like, what was that all about? I'll try to do that in 13 minutes. But first, before, because I know this is as usual, it's either a lot, it's either too much or it's not enough. Like, just raise your hand if anything I just said made any, does that make any sense about the sine and cosine? Just like raise your hand if, oh, thank you, Kai. Okay, Kai is totally in it to win it. All right, thank you, Kai. All right, that's good. I'm going to ask a tricky question, actually. Is there anybody that could put in the direct chat? Just put in the direct chat. If anybody got anything new out of, I mean, if you didn't, don't tell me. My feelings can't handle it. But if that helped at all, like not just if it made sense, but if it helped at all, even if it could have been done in 3 minutes instead of 30, could you just put in the direct chat that if it all addressed any question that you like asked in Google Classroom, just put it in the direct chat, please, just so I don't feel. But if not, well, I guess that's all right. Well, I'm gonna move on. There. And he put, okay. And thank you, Alfred, for putting going public. Thank you. I feel like I just got a Yelp review. Okay, I can now my business will turn a profit. No, seriously. And thank you, direct chat people. Okay. Thank you. All right. And am I fishing for compliments? Yes, I totally am. I mean, I have self-esteem issues too, don't we all? Okay. No, good. Thank you. Good. I'm glad. And for those of you, I promise I'm yelling and screaming about this because I do think it's worth it. Like, I want you to rock your formal reports on the lab. Like, I don't know how harsh of a grader she is these days, but like, I want you to do well on your formal lab. But also, you will see this again, like on you will. It's not like it will help you do work for me later in the semester and in 204. I promise. So hopefully, okay. And the sine cosine issue is like, yes, it's big in 204. And it was a plague for me when I was first doing physics. Like, I remember literally being in college and finding this so annoying. So like, you're not, okay, so it's like but it's a big physics thing. So, okay, fine. So now I'm going to move on kind of for 11 minutes. Okay. So, like one of the two videos then well, was confusing in its own way. What I'm here to say, so I'm not going to do the whole video again right now in 10 minutes, but if you got anything out of that, and thank you, then if you're like me, maybe, well, God forbid. I mean, what you might be thinking is, all right, I get it, but God, like that's a lot. Like that's a lot of yelling and screaming to break up, to figure out the sine and the cosine for MG. And if you got the point, the reason it was difficult or new to choose the sine and the cosine is because we were breaking up MG and MG wasn't on a diagonal line. Like that's what made it confusing. That MG was straight down, and you've never done that before. Like I know that, or probably. Um, so when it raises the question, well, couldn't we have just broken up the other one? Like really? And the answer is yes. We could have left MG alone. And we could have broken up the normal force instead. But what I'm going to try to summarize quickly now in 9 minutes is why that will make matters even worse. Now, I'm not trying to make your life hard, but I'm trying to show you why physics actually does make sense. So go back to the pure free body diagram. Pure free body diagram was this, right? Bah, bah, bah. Actually, I guess the title of this really isn't. Sorry. Okay. Okay. So could we, could we, could we just be like normal people who didn't sign up for physics and just say like, this is the x-axis, like we always expected in math class, and this is the y-axis? Could we just do that? And if we do that, then just break up the normal force? Could we leave x as horizontal and thus, well, and thus break up the normal force and leave gravity alone, for heaven's sakes? We could totally do that. Yes, we could. And here's what happens if we do. If we do that, the component FBD would look like this. Actually, wait, hold on. We would zoom in on the normal force. Well, yes, sorry. We'll zoom in on the normal force. I'm looking at the time. We have 7 minutes. We'll zoom in. So instead of breaking up gravity, we'll zoom in on N, right? So here's N, the normal force. We're going to break it up into two components. This looks easier, right? Like something going up and to the left is going somewhat left and somewhat up, right? And here's the right angle, right? Well, again, I'm going to say this quickly because this is sort of the point of the video, but like, okay, so this is N, and one component will be N of sine of theta, and the other will be N cosine of theta, and I don't know which one is which. If I didn't listen to all of this, I might just think, oh, the x-axis is cosine, y-axis is sine, end of story. But even with the normal force, there's something weird going. Like, look at the normal force. I'm going to do SOHCAHTOA now, right? I'm going to say opposite over, but I have to choose like which of the angles am I looking at? Like, am I looking at the top angle or the bottom angle? Well, the question is, which of those angles is theta? Like, same question as before. Which of those angles is theta? Well, now I'm going to say this quickly because we only have 6 minutes, but if I want to know, so, like, which of the two non-right angles is theta itself, right? The original theta from the left. Well, it's not the bottom one. It's not. How do I know? I mean, it's not. It might look like it is. Because the angle at the bottom, the angle theta at the bottom of the inclined plane, the angle that we want, this theta here, is measured between the horizontal and the ramp itself, right? That's theta. But this yellow line that we're looking, or this whatever color line, this white line that we're looking at here, that's not the track. That is necessarily perpendicular to the track, right? Like, think about that. I mean, I know we only have 5 minutes, but that N is by definition, that's not the track. That's a line that is normal to the track, which means perpendicular to the track, right? So that angle formed between that hypotenuse and the horizontal is not the angle between the horizontal and the track. It's the opposite of that. I mean, it's like the complement of that, right? Like the normal force is perpendicular to the track. It's not. So if the track is an angle of 10 degrees, then the normal force is at an angle of 80 degrees from the horizontal, right? So the angle between the track and the horizontal is the opposite of I don't know how better to say that. But in other words, this angle down here is not theta, it's 90 minus theta. This angle is theta. It's the same problem that we had with the gravity. I don't even know if it's harder to see here or easier, but I'm saying theta is up there at top. Therefore, this side is n sine theta because it's opposite. The bottom side is sine of theta and the adjacent side is cosine. So for those of you who very intelligently asked in the portal, like, I think I get this, but I like need other example. In a way, this is another example of the same idea that your goal in a physics problem is you have to figure out where is the theta that you're focusing on. Once you actually know what the theta is you're focusing, then you just do SOHCAHTOA. Then what you can, and it won't fail you. Don't memorize that sine goes with y and cosine goes with x. Memorize that sine goes with opposite and cosine goes with adjacent, and then put all your effort into figuring out opposite of which angle. Okay, that's what really. So therefore, and I have 3 minutes left. But if you may have to think about this on your own. But if you do think about that, then our component free body diagram becomes the component FBD. And again, this is like not including friction. But once there is friction, you just add it to all this whole situation. I mean, it doesn't change the situation. So the component free body diagram looks like this then. And cosine goes up. Surprise. And I'm not making fun of you. That's new. It was new to me too, but it's just true. So that's our component. So therefore, with 2 minutes left, we now do F net equals MA on each axis like we want, right? So we'll do F of all the Y forces equals MA in the Y. So in the Y axis now, we'll have N cosine theta equals MA. But now here's the thing, and we're just about done. You can't just say MA, because now look, and this is why we don't do this. Like the thing is accelerating along a hypotenuse. That's not either of our axes. We didn't line up our axis with the acceleration. So acceleration has to be broken up. Like acceleration's going like this. Therefore, acceleration has two components. What? Yeah. Is that annoying? Yeah. That's why I don't do it this way. But it's true. So I'd have to say in other words, the x component of A. So n cosine theta equals AMA sine theta. What? And on the other axis, we're just about done with 1 minute left. On the other axis, then, in cosine theta down, sorry. MG, because I'm always making down the positive. So MG down equals N cosine theta up equals MA sine theta. And from the top, it's from the X, and from the Y, we just said in sine theta equals MA cos. Did I just do it backwards again? Sorry. And cosine theta equals MA sine theta. So now when you want to, and we're done, I know it's 1:30. So now when you want to solve for A now, there is a lot of algebra to do because you still have all these sines and cosines. And once you put friction in, there's even more sines and cosines, and that's a lot of algebra. So this is to solve for A, right? Because you got to get A by itself, get rid of all the sines and I did it wrong again. What? Wait. Sorry. And I did it wrong again. Sorry. I mean to say, and then we're done. Sorry. This. Okay. So it doesn't make it any easier to break up the normal force. It's just as hard, if not harder. That's the point. So anyway, okay. Text me if you want to talk about your grade, whatever. Have a great holiday. Have a great holiday. I mean, I'm here if you want any questions, but I'm turning off the recording. Great holiday. Thank you. Have a nice